Think of modern software as a towering skyscraper built entirely out of logic. If one structural beam fails, the whole thing comes down. Testing serves as a continuous verification process, evaluating the product for errors and vulnerabilities throughout the development cycle. When teams bypass this process, the results are severe. In e-commerce or banking, a single unchecked vulnerability allows hackers direct access to sensitive financial data and personal user information. Detecting vulnerabilities early reduces development costs while preventing long-term damage to a company's reputation. Rigorous testing ensures the software powering global digital commerce remains stable and secure against both failure and attack. To evaluate software quality accurately, we map testing along a spectrum of scale and visibility, starting with two parallel models. First is verification, or static testing. On the left, we review requirements without running code. Early verification keeps costs low. Parallel is validation, or dynamic testing. On the right, we execute the software to confirm functionality. These later dynamic fixes demand a higher budget. Testing requires both halves of this equation. Verification answers, are we building the product correctly? Validation answers, are we building the right product? Here we see the software testing lifecycle, running directly beneath the software development lifecycle. Testing requires fewer team members, but equal rigor. The timeline begins early, focusing on isolated test environments and developing precise test cases. A test case is the foundational unit of all testing. It operates as a strict, localized set of rules dictating exactly how a specific system feature will be evaluated. A standardized test document requires exact fields, a numerical test ID, prerequisite conditions, precise operational steps, and the expected results to validate the outcome against. By standardizing these components, the STLC ensures quality control remains a repeatable science driven by precise documentation rather than unstructured guesswork. Once the planning phase concludes, execution begins at the smallest possible scale, where the internal architecture of the software is entirely visible. In white box testing, internal algorithms are transparent. Developers perform unit testing on these isolated parts, verifying specific inputs produce correct outputs. Then, during integration testing, multiple components are connected, verifying they transfer data without corruption. White box methods guarantee internal integrity. You cannot build a stable macroscopic product if the microscopic building blocks are structurally flawed. With the individual units integrated, we shift the scale outward. The foundational code is written, meaning the testing approach must change completely. In black box testing, the internal code is hidden. During functional testing, teams feed a specific input into the system and verify that the resulting output matches the customer's exact design requirements. This execution can be manual, relying on highly skilled human testers, which takes time and budget. Alternatively, it can be automated, using specialized tools and scripts to increase speed and efficiency. In a hybrid approach known as gray box testing, testers utilize partial knowledge of the internal code structure to create highly focused black box test cases. Black box methods strip away developer bias. They force the engineering team to evaluate the final product through the unforgiving, results-oriented perspective of the end user. Yet, a software product can flawlessly pass every functional requirement and still fail entirely in the real world. That requires non-functional testing. We start with performance testing, which measures the software's speed, stability, and resource consumption under varying workloads. During stress testing, we pile extreme workloads onto the system until it inevitably fails, establishing maximum capacity. Next is concurrency testing, simulating hundreds of simultaneous users to identify bottlenecks and dangerous code deadlocks. Finally, testers run regression checks. This guarantees that new updates or bug fixes haven't accidentally broken older, already tested functionality. Functional testing ensures the software works in a controlled laboratory. Non-functional testing ensures it survives the high-volume chaos of the real world. We now leave the rigid, automated lab environments entirely. The final variable to test is human unpredictability. Before public release, an organization conducts internal alpha testing to catch remaining defects. Then, they open the software to random external end users for beta testing in real-world scenarios. This stage includes ad hoc testing. It abandons formal documentation entirely. Experienced veterans perform unstructured error guessing, using chaotic inputs to intentionally break the system. When these unpredictable users find a bug, the resolution procedure is strict. Record the defect, control the issue management, and generate a final report. The lifecycle provides a mathematical baseline for quality, but raw human behavior remains the ultimate, unavoidable stress test. Mapping this complete testing landscape reveals a continuous journey from microscopic unit tests to macroscopic real-world deployments. The structure splits into two halves. On the left is quality assurance. It's preventative, focusing on designing correct processes before code is written. On the right is quality control. It's detective, focusing on executing tests to fix defects in the deliverables. Consistent software quality relies on these two frameworks working in tandem. Quality assurance designs the process, and